Today I want to talk about Q, and Q is a reaction quotient. So it's one of those variables that actually makes sense for why it is the variable it is, because we're talking about a quotient, which means that we're doing some dividing, and a reaction quotient is referring to an equilibrium constant expression. So K is our equilibrium constant, and that K can have a number of different subscripts there. It could be KEQ if we're talking about just kind of a generalized equilibrium constant. Sometimes K is just K. K can be K sub C for concentrations. It can be K sub P for pressures. It can be all sorts of interesting variables, and we'll get into this in future videos as well. But K in general always has the same format. It's the concentration of the products raised to the power of their coefficient in a balanced chemical equation divided by, and there's your quotient piece, the concentration of the reactants raised to the power of their molar quantity in a balanced chemical equation. So when we're talking about a reaction quotient, it's the same thing as K, but the difference is that we don't necessarily know if we're at equilibrium or not. So if we don't know that we're at equilibrium, we can't use an equilibrium constant. But if we have concentration information, or if we have pressure information, or if we have kind of other pieces of information that could get us to K, then it can also get us to Q. And that comparison between Q and K gives us a way to predict which direction a reaction is going to move. Is it going to go further? Is it going to keep producing more products? Is it going to keep producing more reactants? If Q is the same as K, then that means it is at equilibrium. So that gives us information about, given a set of conditions, where are we at in the reaction progression? And this is kind of an important piece because we as chemists like to make predictions about things, and we want to see kind of what is going to happen next. If I need to produce more, am I at the right circumstances in order to do so, etc. So let's take this example. Let's take carbon monoxide and hydrogen gas. We're going to react them together, and that gives me methane and water vapor. My K sub C here is 3.92, so that's a K value that's slightly greater than 1, which means that the products are slightly favored in this type of equilibrium scenario. So if we're given some information about the concentrations that we have, so let's say that we have 0.02 molar of each of my reactants, so reactants are here on the left, my carbon monoxide and my hydrogen, and I have 0.001 molar of each of my products, then which way is the reaction going to shift? Well, the first thing we need to figure out is our K value. So our K sub C here is equal to the concentration of my products raised to their power. So each of these guys is just raised to a 1 because there's one of each of them, divided by the concentration of my carbon monoxide times the concentration of my hydrogen gas. This one is 3, so we're going to cube that guy. And that's going to be my expression, products over reactants. So our Q is going to have the same setup, the same formula. And I'm going to show you some notation here. Q can have the same subscripts here, so we might call this Q sub C. And we'd say that this is going to be the concentration of my methane at a given instant. So sometimes you will see this notation where you have a little I next to it. So the I is for at a given instant. And here's my water vapor at a given instant. And here's my carbon monoxide at a given instant. And then my hydrogen cubed at a given instant. Okay, I think that the I is a little bit unnecessary for a lot of calculations, but for clarity's sake, and just because you're going to run into it depending on kind of where you're looking at in terms of resources, then I'm just mentioning it here for notation. Usually with Q, it's just Q. You don't necessarily always have the subscript there. And again, with these concentrations, if you know you're solving for a Q, it's implied that it's at a given time. You don't know that you're at equilibrium or not. You might be. Okay, so if we plug in these values here, we're given this concentration for each of my products. So it's essentially this squared over this concentration and then that concentration cubed. So it's essentially this concentration to the fourth. And the answer that I get is 6.25. That's my Q. So now I say, well, that's all well and good, but now what do I do? Well, I take this Q value and I say, well, at these given conditions, this is what the reaction looks like. This is my reaction quotient, which tells me where I'm at with respect to equilibrium. And my equilibrium constant says that at equilibrium, this should be the quotient of my products to my reactants. Well, I've overshot that. This is bigger than my K value. And if this is bigger than my K value, I've overshot my equilibrium. I've pushed too far in one direction. And if it's bigger, that means I've pushed too far in the direction of the products, which means that in order to balance things out, in order to reach equilibrium, which is what reactions are driving to do, is to reach equilibrium, then it's going to have to shift towards the reactants. So we'd say that it shifts left, or that it shifts towards the reactants. So when we're talking about chemical reactions, if you know a little something about Le Chatelier's principle and kind of how things shift back and forth when you apply stressors to situations, having too many things on one side or the other is going to cause an imbalance, which is going to cause the reaction to move around one of the other ways. So we can calculate where it's at a given moment. We can compare it to the equilibrium constant, and we can say, well, in order to balance this out, because I've overshot my equilibrium, I'm going to have to shift back towards my reactants to balance things out. Okay, this would probably be 6.3 with sig figs, but you know what I mean. Okay. So, in summary then, if we're thinking about kind of general rules, so like in this last example, if Q is greater than K, we've overshot equilibrium. So our reaction is going to shift towards the reactants, which I like that I wrote products there. Just kidding. Reactants. Other way around. That's what I get for doing my notes in advance. Products. Okay, if it's less than K, what I mean that I haven't reached equilibrium yet. So I haven't gotten to the point where I'm at equilibrium. I'm smaller than that K value, so I need to keep shifting in that forward direction towards the products. Okay, and then if I'm equal to my K, so if Q is equal to K, then the reaction is at equilibrium. Okay, so there's my general rule. Let's look at another example. All right, here's an example. This time I have a heterogeneous equilibrium, which means that I don't have everything in the same phase. In my first example, I had all gases, so I was going to include everything in my equilibrium constant expression. In this case, I'm not going to include my solid because I can't talk about the concentration of a solid. So my equilibrium constant is pretty close to 1, which means that there's a pretty balanced concentration of my reactants and products at equilibrium at this given temperature. Oftentimes you'll see that an equilibrium constant is given at a given temperature because reactions, as we know, are temperature dependent. So the kinetics of them, the rate of them is temperature dependent, and equilibrium is when the rate of two opposing processes are equal. So this K can potentially change at different temperatures because of that relationship to the rate. Okay, so if we have 1 liter of a flask here. So we have 1 liter flask, so picture kind of a half of a 2-liter bottle as an Erlenmeyer flask. And we have this many moles of carbon dioxide and this many moles of carbon monoxide. It says if there's some solid carbon present, and I've heated it up to this 1000 degrees Celsius, will more carbon monoxide form? Okay, so a couple things to unpack here. First of all, if there's some solid carbon present, why is that important? Well, it's important because even though this isn't going to be part of the equilibrium constant expression, because we said we can't have a concentration of a solid, it's, 100% of it is carbon, then I still have to have some there. If I have 0 carbon present, then this reaction can't occur, right? That's what a chemical reaction is. As we said, we need these things and we form these things. And so if we don't have one of those things, then we're not going to form the other things. So even though it's not part of the equilibrium, it's not part of the rate, it's not part of kind of what we're talking about there in terms of concentrations, we still have to have some. So if there's some solid carbon present and we've heated it up, will more carbon monoxide form? So what this is really asking is, because carbon monoxide is our product, is it going to shift right? Is it going to shift towards the products? And the way that we can figure out which way it's going to shift is by using our Q, our reaction quotient. So our K value here is going to be equal to the concentration of my products raised to the power of the coefficient here over the concentration of my reactants. And again, I would say the concentration of my carbon, but that would be 1, so it'd be like multiplying and dividing by 1, so I'm just going to leave it out. So my Q is going to have the same expression, but it's at a given instant. So we could see that little sub I there. And now we can plug in our concentrations. Thankfully, we're given a liter flask, so it's just this number of moles divided by a liter, and we know that with gases, they're going to fill the container that they're in, so that's going to be our concentration. So that's going to be the 0.1 squared divided by my 1.5 times 10 to the negative third. Okay, and when I plug that in, I get 6.7. So again, we get a number that is larger than my K value. So my number is too big. So it's going to, I've overshot my equilibrium. So that means I need to balance it out by shifting towards the reactant. So this tells me, because of this compared to my K value, this is going to shift left. So now if I'm answering my question, will more carbon monoxide form? The answer is no, it's not going to, because it's not going to shift towards the products. So it's actually going to shift and form more carbon dioxide, and that's the way that we would interpret that. So the answer is no, which is sometimes chemistry is a yes or no question. But you have to do some math in order to get to that yes or no answer. Okay. So, reaction quotients, super important when we're thinking about predicting the direction of a reaction and which way it's going to go with respect to the equilibrium. If you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.